this recording, we will work a few examples. We'll start with some conceptual questions. Is it possible to have motion without a force? Okay, I hope we agreed on that. Yes, that's Newton's first law. Whenever something is moving, who cares about how did it get there? But once it is moving, it does not need a force to keep it on moving. So an object can be moving without a force acting on it while it is moving. Is it possible to have forces without motion? Absolutely. For example, we'll take the simple case, a block on top of a desk or on the floor. There are forces acting on it. The normal force, the gravitational force. They are balanced, but it's not moving. Okay, we can add forces. Let's say Christy here, pushing on it this way, and Mark here, pushing on it this way. If they both push with equal forces, then Christy and Mark's forces are going to be balanced, and the gravitational force and the normal force are going to be balanced, so we still have no motion. So it is possible. Is it possible to have acceleration without a force? That, no. How do we know it's no? That's Newton's second law of motion. Sum of all forces is equal to ma. I need unbalanced forces to have acceleration. Without unbalanced forces, I don't have an acceleration. Is it possible to have forces without acceleration? Absolutely. That's the case we talked about before. When the forces are balanced, we don't have an acceleration. Okay. This is an interesting example. Sorry about the graphic. Now, we have an astronaut on Earth. He kicks a bowling ball horizontally and hurts his foot. A year later, the same astronaut kicks a bowling ball on the moon, again horizontally, with the same force. Is his foot going to hurt more, less, or the same? Okay. A couple of things before we answer this. The ball is going to have the same mass. The weight of the ball when it is on the moon is going to be less. The weight is along the vertical. So along the vertical, we are going to have a smaller weight, and of course, to balance it, we are going to have a smaller normal force. Fn is going to be smaller than on Earth, and Fg is smaller than on Earth. It's about 1/6 as much as the value on Earth. Now, the kick, that force for a short time that the astronaut is going to exert on the ball. The kick is going to be along the horizontal, like they told us. So it's going to be along this direction. The kick is going to accelerate the ball and ball along that direction. Now, if we apply Newton's second law, the normal force and the gravitational force are balanced. So the only thing remaining is the kick. Let's call it F kick, Fk for kick, is equal to the mass of the ball times A. Now, in both cases, moon or Earth, that's what we're going to get. The force of the kick is m times A. Since the mass is the same, the force is going to be the same. So it's the astronaut is going to be hurt the same way, of course, you see, assuming everything else is the same. Now, the fact that the gravitational force is less, or in other words, the fact that the weight is less, does not affect what's on the horizontal. The main The main point of this question is to remember forces along the vertical affect only acceleration along the vertical or motion along the vertical, and forces along the horizontal affect only acceleration along the horizontal. They don't mix and match. And here the kick is in both cases along the horizontal. The fact that the gravitational pull is less on the moon is not going to alter that a bit, since our kick is along the horizontal. Okay, now another question. A force F acting on mass m1 results in an acceleration a1. The same force acting on a mass m2 results in acceleration a2, that is twice a1. What can we say about the mass m2? Okay, so remember Newton's second law. This force here is unbalanced, so F is equal to ma1. Here F is equal, this is m1 a1 and this is m2 a2. So we calculate for m1, it's F, for m1, so we are going to calculate m1 is equal to F. Since they are asking us about masses, so that's what we are going to do. And here m2 is F over a2. And since a2 we know it's twice a1, so it's F over twice a1. So I'm going to try to isolate what I have here. That's what I have here. So I'm going to be left with m2 is equal to 1/2 times the term F over a1. In other words, sorry for the space here, in other words, m2 is going to be equal m1 over 2. So the mass m2 is half as much as m1. Okay, now we are going to start working examples where we need to calculate things. Now let's start with this first one. A 20 kilogram mass has an acceleration of 3 meters per second squared. What is the net force? Okay, net force is ma. So that's easy. So 20 kilograms times 3 meters per second squared. So in this case, that's 60 kilogram meter per second squared. That is 60 newtons. Okay, wonderful. That's an easy question. Okay, next. Ashley is pushing a 50 kilogram mass with a force of 100 newtons, while Jerry is pushing it with 70 newtons in the opposite direction. What is the acceleration of the mass? Okay, here it's a little more complicated. So we have a 50 kilogram mass, and then we have Ashley pushing it this way with 100 newtons. So F Ashley is 100 newtons, and then Jerry is pushing it this way, Fg. Okay, let me write the full Jerry so we'll not confuse it with the gravitational force, 70 newtons. And then of course we have the gravitational force Fg, which we can find, we don't need to find it here, but m times g, and we have the normal force. Now the only forces along the horizontal are Fa and Fj. The only forces along the vertical are Fn and Fg. We don't have an acceleration up or down, so these two must be balanced and we will not have to worry about them. We are left with the other two. Now, That means FA plus F Jerry is equal to MA. Now here, the forces are along different directions, so I have to figure out a way of handling that. The way to handle it is to choose one of the directions as the positive direction. For example, if we choose this direction as positive, then my FA is going to be plus 100 newtons. My F Jerry is going to be minus 70 newtons. And that should be equal to my M, 50 kilograms, times the A that I'm looking for. Now 100 minus 70, that gives us 30 newtons, is equal to 50 kilograms times A. So solving for A, so it's 30 newtons over 50 kilograms, dividing both sides by 50 kilograms. So it is 3/5 of meters per second squared, or newtons per kilogram. 3/5, it is 0.6 meters per second squared. Okay, let's try another one. Okay, this is even a little more complicated. What force is needed to accelerate a sprinter from rest to a speed of 10 meters per second in half a second? So we have several things given. This is probably going to be more complicated than any homework problem that I will give you. If I give you something like this in a test, it will be broken down. What is the acceleration and then what is the force? Now, but here, since I'm the one working it, I can handle it. So what we have here, the mass of the sprinter from rest, that's initial velocity, and then 10 meters per second, that gives us the final velocity. And we are given a time, half a second. Okay, now the force needed, the unbalanced force, is going to be MA. So I'm going to need to find A. I'm going to find it using kinematic equations, where A is Vf minus Vi over T. In this case, that's going to be 10 meters per second minus 0 over 0.5 seconds. So it's going to be 10 meters per second over 0.5 seconds. That will give us 20 meters per second squared. That's quite a huge acceleration. So F is going to be 75 kilograms times 20 meters per second squared. So that's 1,500 newtons. Okay, let's try another one. This is also the same level as the other one, and it can be broken into several questions. Okay, now first question can be, so we have a bucket. At the end of a rope, and it is being lifted upward with an acceleration of 4 meters per second squared. The question is, what force must be exerted by the rope? So what are the other forces acting on the bucket? Okay, there is the force of the rope, let's call it Fr, the gravitational force Fg, and that's it. Since it's not touching any surface, there will be no friction, no normal force. That's all what we have. Now, to be able to find the force of the rope, we might need to find F sub G first. Okay. Now, look at what we have here. FR along the vertical, FG along the vertical, but they are in opposite directions. They don't fully balance each other out. That's why we have an acceleration of 4 meters per second squared. Now, if I take the upward direction as positive, then what are we going to get? FR plus FG is equal to M times A. In this case, our unknown FR and FG is going to be a negative number that we'll find in a little bit since the upward direction is positive, and that's equal to 20 kilograms times A. A is positive since it's in the upward direction, 4 meters per second squared. So to find FR, I need to find FG. So what's FG? That's easy. FG, it's M times G. So in this case, that's going to be 20 kilograms times minus 10 meters per second squared, the direction, remember. So it is minus 200 newtons. So I'm going to go back to the top equation. FR, instead of plus FG now, it's going to be minus 200 newtons. And it's going to be equal, instead of 20 times 4, I'm going to calculate it. That's going to be equal to 80 newtons. So solving for FR, I'm going to add 200 newtons to both sides. So I end up getting FR equal to 280 newtons. Okay. So it's a little, again, as complicated as it can get for this level course, but it's something we can handle. But remember, I will not ask you, if I'm going to ask you a question like this on a test, I'll break it into sections. Okay, a few, even more examples. Tommy tosses a ball upwards with an initial velocity of 10 meters per second. How many forces are acting on the ball 3 seconds after Tommy threw it? Okay. So as long they didn't precise it here, as long as the ball is still in flight, there is only one force, the gravitational force. What is the net force then acting on the ball? Actually, man, I just realized it here. This question is missing something. Tommy tosses, let's say, a 100-gram ball upward with an initial velocity. Now, the net force is going to be just equal to the weight. Net force is going to be equal to Fg, since Fg is unbalanced. And Fg is going to be M times G. Now, in this case, it's going to be 100 grams, that's 0.1 kilograms, times minus 10 meters per second squared. So it's going to be 1.0 newtons. Okay, we are going to finish this part with this example. It's a little long example, but broken in several questions. Lori had to push a 400-kilogram fridge with a force of 1,000 newtons before she was able to get it moving. Yet the minute the fridge began moving, Lori noticed that if she kept applying 1,000 Newton force, the fridge would accelerate 1 meter per second squared. Okay? So understand things here. We have the mass of the fridge. The fridge didn't move. She kept on pushing and pushing and pushing, didn't move till she applied 1,000 newtons. But she realized if she keeps on applying 1,000 newtons, the fridge would accelerate at 1 meter per second squared. Now the first question, what are the forces acting on the fridge? before Lori get it to move while still pushing it? Okay, that's a good question. So this is our fridge. Okay. Now Lori is pushing. She's pushing with a force this way. Let's call it FL. Since it's not accelerating in the direction of her push, there must be a force opposing her push, and that force can be only the friction force, static friction force, so F sub F. And then, of course, we have along the vertical the gravitational force, and that's going to be balanced along the vertical by the normal force exerted by the floor. Gravitational force exerted by the earth and the normal force exerted by the floor. Remember, I'm making the distinction all the time between floor and earth. That's important. Okay, now we agreed on this. The next question, what is the maximum static friction force on the fridge? Now, like what we did in the examples before, the maximum static friction force is the force that we need to apply to get it to start moving. And in this case, Lori had to apply 1,000 newtons to get it to start moving. So my maximum static friction force is just 1,000 newtons. Okay. Now, once the fridge started moving, what are the forces acting on it? Okay. Now we'll have a graph, same kind of situation. And the door, we still have Lori. She's still pushing with 1,000 newtons. That's F Lori, so we still have that force. The gravitational force didn't change, it's still there. The normal force still balances the gravitational force, and we know that since we know that the fridge is not going to accelerate upwards or downwards. And then there must be another friction force. The other friction force in this case is going to be sliding friction, since the fridge is going to be sliding, and that sliding friction force is going to be directed this way. What is the net force on the fridge then? Net force, remember, is the sum of all unbalanced forces. Now in this case, our forces are, let me write it, F Lori plus Fg plus Fn plus F friction. And of course, we know that these two are balanced, so we don't have to worry about them anymore. So the unbalanced forces might be Fl and F friction. But then F net, we know also that F net is equal to Ma. Okay, once we know that, now what tools do we have? Which method is going to be able to get us the net force? Is it the top equation or the bottom equation? The top equation would require that we know Fl, which we know 1,000 newtons, and the friction force, which we don't know. We know the maximum static friction, but we don't know the kinetic friction. If I use this alternate look at the net force, I would need to know the mass of the fridge and the acceleration. Both of these are given here, a mass of 400 kilograms and an acceleration of 1 meter per second squared. So let's go back. So a mass of 400 kilograms and an acceleration of 1 meter per second squared. So my net force is 400 times 1, so it is 400 newtons. That's my net force. Now, what force should Lori apply then to stop the fridge from accelerating? Okay. So, what force should Lori apply to stop the fridge from accelerating? Okay, one easy way to think about it, my net force is, we just found it, 400 newtons. So Lori is applying 400 newtons more than what we need. So if we take 400 off of the force that she's applying, we'll find out how much she needs to apply. Another way to look at it, let's find the friction force here. What Lori needs to do is apply a force large enough just to balance the friction force. Remember, what she's trying to do here is stop it from accelerating. Stop it from accelerating. That's not stopping the fridge, just stopping it from accelerating. It's going to continue moving at constant velocity. So to do that, then let's find the friction force. In the previous question, what we had was, we said our net force is 400 newtons, and that's equal, let me write the equation first. F net is equal to FL plus F friction plus Fg plus Fn, and we said these two are balanced, so we don't have to worry about them, and we are left with 400 newtons is equal to FL, which is 1000 newtons, plus FF. So FF is minus 600 newtons. To have no acceleration, FL has to be equal to FF, so the new FL is to be equal to 600 newtons. Question then, what if Lori decides to let go of the fridge? What would the net force be? Okay, we saw that in the simulation. So then, if Lori lets go of the fridge, what are the forces acting on the fridge now? Gravitational force still there, normal force still there, and the friction still there. There is no Lori. So again, if we apply our Newton's second law, F net is going to be equal FF plus Fg plus Fn, and again these two are balanced and we don't have to worry about them, so F net is just the friction force, and which is minus 600 newtons. What would be the acceleration of the fridge then? If I know F net, which we said is minus 600 newtons, we know that F net is equal to ma, which is 400 kilograms times a. So we solve for a. 400 kilograms times a is equal to minus 600 newtons, and a then becomes minus 6/4 meters per second squared, okay, or 3/2, so it's minus 1.5 meters per second squared.